Good morning and good afternoon, depending on where you're joining us from today. Thanks so much for being with us. And I know we're already 2 weeks into our new year, but Happy New Year. We appreciate all of you spending some time with us as we journey into 2022. This is our second episode of our new Two Talk series, and today we're taking a deeper dive into fuzzing. So get ready to follow along and learn more about why you should add fuzzing to your software testing toolkit. I'd like to introduce our speakers for today. First, it's my pleasure to introduce Matt Keeley. Matt is a senior security consultant at Bishop Fox, specializing in application penetration testing, product security reviews, and source code analysis. Matt is an avid security researcher and is considered an internal subject matter expert for product security reviews. He was also recently quoted in the IT Business Edge and interviewed on fuzzing on the InfoSec Prep podcast. Matt is a graduate of ASU, where he co-founded the cybersecurity club DoubleSec. And we have Joe Sechman, Associate VP of Research and Development, where he's responsible for nurturing a culture of innovation across Bishop Fox. With more than 20 years experience, Joe has amassed multiple security certifications, delivered several presentations, and has co-authored many industry publications. He is also a contributing inventor to 9 granted patents in the field of automated application security testing. And I'm Jerry Kirshner, Senior Marketing Manager here at Bishop Fox. So let's get the buzz on fuzz testing. And with that, I'm going to hand it over to Joe.
Thanks, Jerry. Really excited about today's topic. Matt is definitely one of the industry experts here in this topic, and we're really excited about the content today. To get started, Matt's going to cover some of the basics of fuzzing, how fuzzing works, provide an introduction, and no tool talk would be complete without listing some popular fuzzing tools. At the end, we'll also cover a quick demo of fuzzing in action, and then save some time at the end for Q&A, but feel free to submit any questions as they come about. With that, I'll hand it over to Matt.
Awesome. Thanks, Joe. So the reason why everybody's here. So what is fuzzing? Fuzzing is more or less a technique for researchers, developers, security people, pretty much anybody in the software realm or having to deal with software. And what fuzzing is where you can send arbitrary inputs to a program with hopes that the program app acts in an abnormal way. So if the program crashes, if it acts really bizarre when you send some sort of arbitrary input into it, that's sort of what the process of fuzzing is. And so this typically happens in 2 different ways. You have black box fuzzing, which is just throwing things into the program in hopes that it will crash, it will have a race condition, it will do anything that it's not supposed to. And with black box fuzzing, you don't have the source code, so it's a little bit harder to get further code coverage, to get the same sort of feel or the same sort of vulnerabilities as you would out of white box fuzzing. So that sort of jumps into the white box fuzzing. And this is where all the source code is available. A lot of times you can actually compile the binaries themselves to work with Cling or to work in your favor. You can also edit the code, and that will allow you to add different paths and allow for more code coverage into the applications or binaries themselves. And so fuzzing isn't just for binary analysis or web applications. It can be used on pretty much any type of software. So at Bishop Fox, we do fuzzing for different automotive systems, different web apps, different binaries, network protocols, things of that nature. And so some of you are probably wondering, what's the whole goal? Why should I fuzz this? What is fuzzing? Why does it work? Why should I do it? Ultimately, you want to fuzz a program to make sure and to thoroughly show that your program or your software can interact with whatever a user throws at it. So if a user can throw bad input at the program and it crashes, that's you don't want that. And so more or less, like, what we're trying to look for with fuzzing is for crashes, infinite loops, or just otherwise known bad behavior. And some of this can be memory corruption problems. You can have cryptography problems, but essentially we just want to make sure that the program is as robust as possible and that it will hold up against whatever is thrown at it. So a little more onto what you can find with fuzzing. Again, these are more geared toward like binary fuzzing. So, things like memory corruption issues such as heap overflows, stack overflows, out of bounds reads, out of bounds writes, double freeze, use after free vulnerabilities, things of that nature. For web applications specifically, a lot of these will also exist, not so much in the memory corruption space, but you can find race conditions, which will often lead to things like denial of service attacks. Sometimes just sending arbitrary input to a program on, whether it be a web app or via CAN bus line, it will just create it. It'll essentially make it blow up, right? It won't work. It'll cause a denial of service, and it just won't progress anymore. There's a bunch of other things that fuzzing can help you find, such as algorithmic attacks, information disclosure, but the list is really never ending with what you can find with it. And so this is sort of where we get to like how it works. We just talked about more or less like why you should do it, what are sort of the goals that we have. But to sort of demonstrate like exactly what's happening with smart fuzzers specifically, we created this illustration here, and I'll sort of walk you guys through it. So we have this input at the top, and this was input that the user sent in to a binary application or web application. It doesn't really matter for this use case, but the user sends in the word test. And so what our function below does is it checks each letter of test to ensure that it matches, or to check if it matches a different character. So as you can see, let me get the pointer up real quick. If you can match up the F to the first letter, the U to the second, the Z to the third, and the Z to the fourth, then we will actually hit this yes case and cause a crash in the program. And ultimately, that's what we're going for here. We're trying to find the crash. This is a very basic example, but with smart fuzzers, it can be quite complex, and this is essentially how it does it at a high level. So as we can see, obviously, test does not match fuzz. T doesn't match F, E doesn't match U, so on and so forth. So what's going to happen here is we're going to hit that no case and just exit the program. So we didn't cause a crash. We didn't find anything, out of the ordinary, any bad behaviors, anything like that. But what the smart fuzzer does well is it will sort of figure out on its own, like, okay, we didn't get any here, we didn't get any here, and it'll start to generate, without getting too in depth on how it all works, but it'll sort of generate its own test cases and sort of mutate those to try to find better paths. So this is sort of where it goes, right? So we tried test didn't work. We hit the no path immediately and nothing happened. So as the fuzzer works, it will generate new inputs, new test cases and things like that. And so it mutated to func now. So we started with test, now it's func. We see that the FU and func do match our two test cases. However, we don't match all four of them. So we're still not going to hit the yes case, but we are getting closer, right? So we have two that are matching up. The fuzzer's starting to get it. We're starting to go a little further along the path, but we're not quite there. So we still hit the no case and exit out of the program, but we're getting somewhere. We're moving along. And so the last test case is fuzz, right? So once we hit fuzz, we see that all of the parameters that we have here, the FUZZ matches up top, FUZZ, and we hit the yes case. And so this is sort of showing more or less like the fuzzer will arbitrarily modify and mutate the corpus and the seeds to more or less get further code coverage into the program. And so when we do send the fuzz, we can cause a crash to the program and then triage and debug why this happened. And then, a lot of times this would be with memory corruptions or race conditions or, whatnot to cause the crash. And so once we get to this crash, we can triage this, or if you're a red teamer, you can do like a PFC and whatnot. We have any questions so far, or I think we're...
Actually, Matt, you brought up, I think you brought up a term that's near and dear to my heart in code coverage and testing and methodology. One of the questions that comes to mind is, how do you know when you're done fuzz testing?
Yeah, so the job is really never done. The goal of fuzzing, especially with a lot of smart fuzzers nowadays specifically, you try to get the best code coverage as possible. And for those of you out there, code coverage is essentially how far into the code base can you get. And you can even dive this down specifically to like what line you got down to within a particular program. For our example here, it's relatively short. It's one function. So there's not really much here, but if you think about it in like a really large database, the code coverage can really go forever. And so you have different things like symbolic execution that will help you sort of guide the code coverage further, but you're not always going to get to the very end of a program. And a lot of times, like, that's sort of the nature of fuzzing. It can't go all the way through every single time, but depending on the size of the program and the use cases, you can completely fuzz a program inside now. So. Cool.
Makes sense.
All right.
Thanks.
Yeah, no problem. So there's no more questions. I'll sort of jump into some of the more popular fuzzing tools. Like all of these fuzzing tools, there's just so many buzzwords that are thrown around, right? Like brute force fuzzer coupled with an instrumentation guided genetic algorithm. It's a lot of buzzwords, really doesn't make a whole lot of sense if you're new to a lot of this stuff. So essentially, like I said, what a fuzzer does, you're throwing inputs into a program or a web application or whatever you're trying to fuzz in hopes to cause the crash. So that's pretty much what all these fuzzers do, but it's a little bit specific each time for each of them. So with AFL, it works really well with C, C++ programs. Can work with others, but that's typically what you want to use AFL++ for. Today, we're going to use AFL Fuzz, which is like another distribution of AFL. There's probably like 25 or 30 different types of, or different distributions of AFL. But more or less, that's how that works. BooFuzz is written in Python. It's pretty good with network protocols. It's a really popular tool. A lot of people do it for binary fuzzing as well, but you don't have to. So if you have anything running with like sockets or any sort of like web connection protocols that you're wanting to fuzz, BooFuzz is really good for that. And the last one we have up here is Fuzzily. This works extremely well with any sort of JavaScript applications, web applications, and things like that. But overall, these are just 3 pretty popular fuzzing tools. There's about 100 of them out there written for every single language. And they do a whole bunch of stuff, right? It's not just binaries. It's not just web apps. You can do things like fuzzing CAN bus systems for automotive cars. You can fuzz, like network protocols, weird network protocols, and you can even fuzz situations and things like that. A good example of that would be like a power grid. You can actually fuzz situations to see, what happens if a squirrel eats line and a part of a power grid goes down. It's a really weird case for that one, but it is a thing. You can fuzz just about anything so long as you have the fuzzer set up correctly and you have a proper harness for it. So without further ado, oh yeah.
Hey Matt, sorry. Right before we pivot over to the demo, we did get another question in off our conversation a moment ago. I feel like fuzzing is really just brute forcing, and sometimes that kind of technique does not always lead to quick code coverage. How long should I let it run? Does that time vary? Very similar question, but I think it's a bit nuanced in that regard.
Yeah, so ideally, running the fuzzer for longer periods of time would be best. So a lot of times what we see in like CI/CD pipelines, we'll see that every time a developer pushes code to the GitHub repository, GitLab repository, that you can automatically integrate the fuzzer to run. However, sometimes that's really resource heavy, which isn't always the best thing to do. So ideally, what you would do is every time you make a lot of big changes, so long as you have custom harnesses, and that's really what the big thing we do at Bishop Fox is. So we'll take a piece of software and we'll write what's called a harness for it. Essentially, what the harness does is allows you to get further into the program without, or, like generally where the program would not take you otherwise. So for example, like if you have a function pretty deep in your program that user input doesn't really see unless you hit all of these weird test cases, the fuzzing harness will help you get there. So to fully answer your question, it's not always brute forcing. A lot of times with symbolic execution, it'll actually, I'm going to jump back one here to show the demo real quick. So back to the demonstration we were giving, you can actually follow a lot of the code paths. And so the fuzzers with things like symbolic execution will actually try to hit as many code paths as possible and sort of solve the, like we did here, we solved the problem where we're trying to hit the word fuzz to continue on into the program. And so that's a lot of times what fuzzing will do. It's not all brute forcing. It's really, really not. It tries to get as much code coverage as possible by figuring out all the paths that are available to us.
Okay, while you're spinning up the demo, I've got a couple more questions, but I'll start with this one, as it's indicative of a conversation we had about a month or two back. When you say web application, can you give a little more detail? For example, what distinguishes Fuzz tools from Burp Suite? By web application, do you mean an app that uses WebAssembly, specific communications protocols, et cetera?
Yeah, so really what a web application is, Burp Suite actually has a fuzzer built into it. That's what the active ++ scan, that's what it'll do. It does fuzz all of, I don't want to say all, but it does try to fuzz as much as it possibly can in terms of like what a user can input. And a lot of times with Burp Suite, it does fuzz the web applications themselves to more or less find the cool SSRF vulnerability, to find the XSS, reflected XSS usually, but to find the XSS vulnerability. So what it is doing is it is fuzzing, but it's more or less doing what a dumb fuzzer would do. It has a predefined list of like generated inputs. Like for example, with the intruder product that they have, if you're trying to do XSS payloads because you think, like a web page might be vulnerable to cross-site scripting, they actually have a payload set of XSS, payloads that you can inject into a spot into the web application. So more or less, like web applications are pretty much any sort of like website, can be smaller web apps, could be just single function web apps. You can fuzz those as well, but pretty much like any website, anything that's hosted on HTTPS or HTTP that you can interact with in some way, or that a user will interact with in some way.
Here we've got a couple more. Is there any benefit to roll my own fuzzer, or should I look to use proper fuzzing utilities like what you recommend? And a follow on to that, does Bishop Fox have anything comparable, or I guess recommend anything comparable to ForalSecure's Mayhem?
Bishop Fox doesn't have a product similar to Mayhem. However, we use a lot of the common tools that are already out there. There's not really a big point in reinventing the wheel. There's a lot of big companies out there that are creating some amazing fuzzers that, that can even compete with big projects like the Mayhem project. Specifically, Google, Facebook, all of your Fortune 10 companies do have a lot of their own internal fuzzers that they use. Google has a project called OSS Fuzz it's been blowing up here in the last maybe 6-7 months or so. But yeah, I wouldn't go reinventing the wheel. There's a lot of fuzzers out there. They do a lot of great things, and they'll find a lot of the similar vulnerabilities that you're looking for. What Mayhem does specifically well is it can identify code paths in a way to where if they sort of more or less run out of code paths, they can still dive deeper into the firmware and still get further code coverage, whereas a lot of fuzzers don't necessarily have that capability and technology. So Mayhem definitely is a great option, but there is a lot of other great options out there, such as Google, such as AFL. It really depends a lot of times on what you're trying to fuzz, right? Like AFL is probably not going to work well if you're trying to fuzz like a CAN bus for any sort of like automotive cars or things like that. Whereas like it's also not going to work on a website. But you do have things like Fuzzily that works perfectly with JavaScript or fuzzes websites specifically. So I would recommend, looking out there, trying to find the tool specifically that fits your web application or fits your binary or fits whatever you're trying to fuzz, and start working with that one. The big thing with that is getting the harnesses set up so that the program can get further code coverage and code execution. And yeah, right now, can you guys see my screen okay?
Yep.
Okay, cool. Yeah, we're just running the install script right now. We'll answer some more questions while this finishes up here in the next minute or so.
Okay, we do have one question, I think more administrative. Plan on posting this to your YouTube channel. Would be nice to re-review these presentations. We do record these, and they will be available. More information will be at the end of this session. Another one: are there any good CI/CD solutions for fuzzing?
Yeah, there's a ton. I mean, there's almost too many options out there as well. But for what we typically do, you can integrate things like AFL or Cling or anything like that actually into GitHub, which makes it really easy for developers, really easy for anybody in DevOps. Essentially, once you push your code, it automatically runs the fuzzer on GitHub side of things. And in turn, doing so, you have a separate fuzz for every time you push code into your database. And this works really well on more or less, on big projects, on smaller projects. It doesn't really matter when you're doing it. The hard part with that is you can only fuzz it for so long. Running your own infrastructure for fuzzing your code would be the best option in a perfect world, right? A lot of times it's just not possible for smaller companies to do, especially trying to get all their own infrastructure set up, having the code automatically push up to the fuzzer, running that for a few days, then, sort of diving deeper into the results and things like that. But yeah, great question. Perfect. So now that our script is pretty much done installing, today for the demo, it's going to be a pretty high level demo. We're not going to dive super deep into the exploitation side of things. We're just going to focus more on the fuzzing side of things. So without further ado, for today's demo, we're going to be fuzzing a binary called object dump. More or less, let's run object dump. More or less what object dump does is it will display a lot of information about a binary. And it can also disassemble binaries, give you the high level disassembly of what the binary is doing, and then you can go through the code like that. And so for like an example, we run object dump on let's do like the cat binary, right? Oh, I just can't spell. Cool. So as you can see here, we get a bunch of information back about the binary, all of the sections that it has when it tries to disassemble it, and things of that nature. So this is the binary that we're going to fuzz today. It's pretty basic binary, nothing too incredibly complex, but essentially this is what we got. So for bin utils, that's where the binary comes from a bin utility project. And it also comes with a bunch of different binaries. What we did in the little demo before is we were actually compiling it with AFL Cling, and that will allow us to easily fuzz the binary. So as we can see here, this is our compiled object dump binary, and this is what we're going to fuzz today. So let's go back here, clear that. So also we can see in our inputs folder, this is called a corpus. Essentially, it's a bunch of test cases that we want the fuzzer to use and more or less mutate to come up with some new inputs, right? So if we cap the second test case, we can see that we're just creating a binary with more or less the content of this, right? It's just a bunch of random characters, random symbols. Some characters don't even come back with ASCII, but that's essentially what we're going to use as our test cases today. And then the fuzzer will actually take all of these test cases, mutate them, and see how things go for that nature. So let's just jump right into it. So first we're going to run the AFL fuzz command. We're going to specify our test cases, which is in our in folder. We're going to specify a folder that we want all of our output to go to. That's our out folder, as we can see here. There's nothing in the out folder. There's nothing, nothing to hide there. But yeah, the out folder is just an empty folder. And then for our binary specifically, we are going to grab the installer bin and object dump. And so what we're going to do with object dump is we're going to do a -s. And what that does, we'll run it here. Just go like that. -s actually provides the full content, including all sections requested of a given binary or a given file. So that's what we're going to do, and that's what we're going to fuzz. So next we need to tell the fuzzer specifically where we want it to fuzz in our program. So we're just going to fuzz this user input that's provided to the object dump binary. And to do that, we're going to use the two @ symbols. Nothing crazy. And we click enter. It sends us a bunch of warnings. It's not a big deal. And says, let us ready, set, or all set to ready and roll. So this is the dashboard that you get with AFL. Really nice, really simple, really neat. It tells you how long it's been running, and it gives you more or less the overall result. So in the last 20 seconds or so, we've already found 3 unique crashes in our binary. And again, these crashes can be things like buffer overflows, like heap overflows. Any way that we cause the binary to crash is what we're finding in these unique crashes. And by unique, it means that we've come up, or the fuzzer has come up with a unique input that has caused this binary to crash. And so we can let this run for, even now, we could let it run for hours, we could let it run for days. Ideally, when you're fuzzing big programs, big binaries, any sort of big software, you'll want to let it run for a couple of days. A lot of times, it's too hard to do. It's too much resources allocated. So less time is often needed, but in an ideal world, that's how long we run it for. But while this is running, we can actually go back and see what we have in our out folder. Clean this up a little bit. All right, so we can go into the crashes folder, and this is all of the files that we have here that actually caused our program to crash. So if we cat one of these out, right, we can see that this user input specifically caused our program to crash. And to confirm this, we can go install dir bin object dump. We can specify -s, and then we'll just grab the first one off the top. So again, what we're doing is we're just running the binary now, specifying that we want the -s option, which will give us the full content. And then we're telling it what file we want it to use to read this. And so when we run this, we see clearly here that we have caused a segmentation fault within this binary, and that is our crash. So once we get to this point, right, there's really two routes. If you're on more of the blue teams, the DevOps, the software development side, this is pretty much all you need to start rolling with it, and it's kind of where the fuzzing ends in terms of just general fuzzing, right? So we've identified that we can cause the program to crash. We haven't really identified why the program is crashing, but that's where, this is at the point where, like in the code coverage specifically, we can see, okay, we caused a crash on, this line in the code coverage, and it, here's our segmentation fault. And so as a blue teamer, you sort of triage the problem to see specifically why it crashed, right? So given this input, you would go back through, look through your program, see where it got to in the program in terms of code coverage and things like that, and then be like, okay, this crashed because we were only allocating, even for the name, right? If we were allocating a character array with 10 characters as the maximum limit, and we gave it like 25 here. So again, the crashes can be things like overflows. It can be anything that really causes it to crash. So race conditions, overflows, many memory problems, things of that nature. So for blue teamers, that's pretty much where it ends after you triage it, figure out why it crashed, and then figure out how to fuzz it even better, right? Can we get further into this section of the code? Is there pieces that the fuzzer missed? Can we generate custom harnesses and things like that? From the red team point of view, a lot of times, the whole fun and the rabbit hole that I often fall down, once you get the segmentation fault, a lot of times it's just a ton of fun to more or less try to figure out why. If it's a buffer overflow, you can come up with a proof of concept and potentially get that cool reverse shell back or fully compromise a system because of it. So weaponizing these things on the red team point of view is extremely possible, and attackers will do it. That's why fuzzing is extremely important for any CI/CD or any software development process. Yeah, that's pretty much what I got for the demo.
Okay, thanks, Matt. We've got several questions that have come rolling in during the demo. I'll start with the one that I think is most fresh on the mind. Does the dashboard show the specific reason for the crash, like the seg fault?
No, it doesn't. So the dashboard specifically will just show the number of unique crashes and show that a crash occurred. However, if you were to take, the binary itself, run it with GDB, you can still specify your input file with that. Then you can fully debug it and see why it crashed, where specifically in the memory it crashed, and things like that. Some smart fuzzers as well, you can hook directly into programs like Binary Ninja. And that will allow you to walk through line by line and see specifically like, okay, this is the line that the program crashed on. Why? And it more or less leads you to the question. A lot of times it's not the specific line, but it's more or less the function that you're looking at for that program to figure out why it crashed.
Okay, we had another astute observation during the demo. Just curious, how did your CPU hit 150% according to the dashboard?
Well, you see, my computer is a little low spec. It'll try to, and that's why I don't know if you guys can hear it, but my computer sounds like a jet engine right now. But oftentimes you can specify. This is, I believe, it's just one core for this. But you can specify specifically how many cores you want in the CPU to fuzz these things. What big projects will do is they'll actually use multiple machines and then split up the fuzzing work across multiple machines and have all of those sync back into one dashboard. So the fuzzing process isn't isolated just to one machine. You can actually distribute the load across collage of machines.
Okay. One other question here. What tools would you recommend for specialized network protocols? Any opinion on Peach Fuzzer, now GitLab protocol fuzzer community?
GitLab one's really good. It just really depends on what you're trying to fuzz. For a lot of the network protocols that we use here at Butcherbox, we'll use BooFuzz for some of them. We do have some internal tools that we use for some of our bigger network-based projects. But more or less, GitHub's got a great fuzzer, especially, or GitLab, I'm sorry, not GitHub. Yeah, like more or less, like there's a lot of network protocol tools out there. You just got to find the one that's going to work best for your project.
Okay. All right, a couple more questions here. And just as a time check, I know we're running over just by a few moments here. We've got several questions in here. If we don't happen to get to every single question, we will indeed follow up. Feel free to drop us a line with any of these communication channels that we've got up on display here. And if I don't say thank you for attending at this point. This is, again, another exciting topic that we wanted to make sure that we covered here. And also, thanks for attending, and keep an eye out for the next tool talk that we'll be doing next month. We're looking to finalize the topic here shortly. And with that, what I'll do is I'll continue on answering the questions that we've got here, or asking Matt these questions, and we can proceed until we've expunged the queue. Okay, one question that I think is an interesting question that's more philosophical in nature, but a good question in all the same, is, are there situations where fuzzing is a bad idea? Why not fuzz everything?
Yeah, well, a lot of times pen testing is a bad idea depending on the environment as well. So for things like production, I wouldn't recommend fuzzing in production. If you can set up a staging environment that interacts and works the exact same way as production, I would recommend doing that, right? Like with pretty much all software, you always want to make sure it works perfectly and as expected in a staging environment before you push anything to production. And sometimes when you push things to production, and it, maybe a pen test, even with, as we brought up before, like the burp active scan, we've tested some systems where, even active scan will just bring down the whole system and cause denial of service. So, expect if you fuzz in production, it's not always going to happen, but just, expect the worst in terms of, what's going to happen in that aspect.
There's definitely a risk there. Okay, when you use the fuzzer with your code, how does the fuzzer track code coverage? Does it do something around inserting debug symbols, or is it a more complicated technique?
It depends on the fuzzer itself. The short answer would be yes, the debug symbols are extremely useful, and a lot of more or less like the binary fuzzers will do that. A lot of the bigger fuzzers, like or the privatized fuzzers, like example Mayhem. They have their own way of doing all that. Really cool process, but yeah, more or less the debug symbols are pretty big for any of these open source ones.
Okay, and one of the tools that that you had mentioned and demoed, is there a huge difference between AFL and AFL++?
Yeah, well, we actually used AFL Fuzz for this one, but yeah, I mean, there's so many different distributions of AFL. You know, it's almost never ending at this point. AFL was like the original product. I believe it was a team of people that made it a little while back. Recently, AFL is sort of outdated in terms of what all it can do. There's a lot of good alternatives like AFL++, AFL Fuzz, and I think there's like 5 or 6 more with AFL in the name. But recently, AFL, it was more or less outdated. And so I believe Google bought the project and pretty much changed it over to AFL++. And so Google's team has been working on that, trying to build it up, making sure that it can perform with some of the top fuzzers out there.
Okay, and just 2 more questions left. How is your AFL instance getting so many executions per second? It seems when I use the executions are really slow.
Yeah, it's a good question. So because this is a smaller binary, we're getting a lot more executions per second. Again, right, it depends a lot on, you know, sort of more or less the hardware that you're using, the type of binary that you're fuzzing, and really what all you're doing. So typically when you get really slow execs per second, you may be working with, you know, machines that don't have as much CPU power. Generally speaking, this isn't a whole ton in terms of just fuzzing standards. I believe this is just running off of my MacBook CPU. But ideally, you know, setting up multiple fuzzers, trying to use distributed systems, and trying to use harnesses for different parts of your program. I didn't really touch on that before, but what we do at Bishop Fox is we'll actually take a client software, and we won't create just one harness that's a catch-all that works for everything. We'll try to sort of break the software, break the programs down into multiple pieces. And we'll treat each piece separately and then create custom harnesses for each of those to try to fuzz those and get further code coverage and find more crashes.
Okay. I think this was in one of the other chats. What compiler was used to compile object dump?
I used AFL Clang specifically because this was more or less like a white box assessment. Yeah, I'll actually do this one for you. Let's go to install.
I think you may need to share if you want to share.
Oh, I'm not sharing. Oh, nice. Yeah, so we're using, I believe it's Fast AFL that works with Clang. So it's just a Clang install for that. But it integrates directly with AFL, which is why we can fuzz this so well. If we wanted to use a different approach for that, like a black box, we can still fuzz the object dump binary using like the normal compilation for that. But it would be more or less like a black box approach for that. It's a little harder to fully identify the code coverage with that.
Okay. Well, thanks everyone for attending, and thanks everyone for sticking around this long to listen to the questions and the answers from Matt. Matt, thank you very much for your time today and going over fuzzing. Once again, if you think of questions after this, after we hang up here, feel free to reach out to us here, and we will be certain to get back in touch with you. That was a tongue twister. Thanks everyone. Enjoy the rest of your day.
Thanks, guys.